As the syllabus says, base value for each quiz is 75 points. As the syllabus also says, I purposely build into each quiz and exam a bunch of earnable extra credit points, because this stuff is tough. I want to give you the chance to show me that you're on top of it. But if you're not quite on top of it, I still want you to have the opportunity to make a nice, fat, good grade. $148 points available. That's almost twice 75. And remember also, the syllabus tells you, I keep score strictly on the basis of total points. So don't ask me about out of, because out of doesn't mean a damn thing. Out of is a percentage, and I don't do anything with percentages. Percentage-wise, if tomorrow you make 75 points, with 148 points being the total value of the quiz, from a percentage standpoint, you made 100%. You got that? So anything above and beyond 75, and I'm sure many of you will in fact earn that, that just goes into your bank, earns interest for you, adds to your total point accumulation. Well, this will be your first point accumulation. And as the syllabus says, once you get to a certain number of total points, you've established an A. I forget what that total point value is for this term. Who cares? It's in the syllabus. Now, I made a goof in my commentary during last class, discussing K values and what they mean. I made the erroneous statement that the K value of 1 means the reaction extent for the reaction on proceeding to equilibrium is 50%. There are cases where it is 50%. But K value of 1 in and of itself is no guarantee that a reaction extent is 50%. More on that, when we get to this question 825, where the acid in question has a K value of 1.0. I mean, the Ka value for this acid is 1.0. So there's a consideration of a system for which the K is 1.0. Now again, we're still covering territory which most of you covered. But because of the damn fire alarm problem last week, I want to make sure everybody gets the same stuff. Question 1820. You now know about Ka and what it means and how it's defined. Kb, what it means and how it's defined. You know about how to read the acid-base table. You know to look at the acid-base table and decide which acids listed are categorically strong, weak, and so weak that they cannot function as acids to a measurable extent in water. Same for bases. You know how to write equations for reactions involving these acids and bases, and to determine whether or not such reactions proceed to a large or small extent. You think I might ask about some of that tomorrow? Don't think otherwise. Now, when we get to K's, then we're in position to really get at the ultimate nuts and bolts aspect of acid-base chemistry, where from a quantitative standpoint we begin to analyze a system. Question 1820. Two solutions. Half molar to 2 sig figs ammonia solution and sodium acetate solution. When you write your PSI, you see this is ammonia and water. That's sodium ion, acetate ion, and water. Ammonia is a stronger base than water, so this solution is basic. Sodium ion has no acid-base properties in water, so we don't care about that. Doesn't have any acid-base properties, Bronsted acid-base properties in any system. Acetate ion is a weak Bronsted base, so this system is also basic. Which of these systems is more basic? The ammonia solution. Why?
Ammonia is a stronger base.
It's a much stronger base. The acid-base table tell you that, which of course is confirmed by the Kb values for the respective bases. 1.8 times 10 to the minus 5 for ammonia, which you get from Kw divided by Ka for the conjugate acid of ammonia, which is ammonium ion. And Ka ammonium ion is 5.6 times 10 to the minus 10. That information is available for your use on the acid-base table. Acetate ion, Kb is 5.6 times 10 to the minus 10. A much weaker base than ammonia, as shown by the fact that the Kb value for acetate ion is a heck of a lot smaller, which means the pH for the ammonia solution is a lot higher than the pH for the acetate ion solution. How do you calculate pH? Or PHO, who cares? Once you know pH, you know PHO. Just like once you know hydronium ion molarity for a solution, water solvent, you also know the hydroxide ion molarity. Kw allows you to know such. Well, I've written here the chemical version of Kb for ammonia, based on our generalization, since this is a single solute system, x squared over m sub I minus x. In this case, the m sub I value is sufficiently large such that when you subtract x from it, which in this case will be the ammonium ion molarity as well as the hydroxide ion molarity, m sub I minus x will remain as m sub I. So this is easily solved for the hydroxide ion molarity because it's half of this, which is 9.0 times 10 to the minus 6, the square root thereof. Gee, that's tough. 3.0 times 10 to the minus 3. There's the hydroxide ion molarity. So from that you get pH, PHO, hydronium ion molarity, whatever you want. Is this a solution to which x squared over m sub I minus x also applies? You bet it is. Sodium ion's in there, but that has no impact on pH, so we don't care about that. So practically speaking, from an acid-base standpoint, this too is a single solute system. Now indeed, in this solution there's also water, which is a Bronsted acid as well as a Bronsted base. You think it's possible under certain circumstances that water can affect the measurable value for pH? You're damn right. We haven't got there yet though. We'll get there. A few more conversations. Not this case. So you know what to do with this. 1821. Can you read the acid-base table? You're dealing in laboratory with a solution, 1 molar ammonium hydrogen carbonate. PSI, ammonium ion, hydrogen carbonate ion, water. So we look at the acid-base table. See that ammonium ion is found to be an acid stronger than water. Well, it's not a strong acid at all. It's quite a weak acid. Ka ammonium ion is 5.6 times 10 to the minus 10. So now we assess the properties, Bronsted-Lowry acid-base properties of hydrogen carbonate ion, which we already have done. In the acid-base table we see that hydrogen carbonate ion shows itself also to be an acid stronger than water. K is 4.8 times 10 to the minus 11. Ka for hydrogen carbonate ion. But in past conversation for hydrogen carbonate ion, we came to realize that if you make a solution where hydrogen carbonate ion is the only principal species in the system which affects pH, the solution will be basic, not acidic. Because Kb hydrogen carbonate ion, which is Kw divided by Ka for quote-unquote H2CO3, and gives the number 2.4 times 10 to the minus 8, is a number that's bigger than Ka for ammonium ion. So again, now that we've got the data before us, In this system, the strongest acid present in high concentration is what? Ammonium ion. Ka 5.6 times 10 to minus 10, which is bigger than Ka for hydrogen carbonate ion. But in this system, the strongest base present in high concentration is hydrogen carbonate ion, with Kb 2.4 times 10 to minus 8. So is this solution acidic or basic? Basic. Because Kb hydrogen carbonate ion is a bigger number than Ka ammonium ion. And the initial molarities of these two species are the same. Now then, another aspect of significance of K value. Will this solution be mildly or strongly basic? Let's define strongly basic as a solution for which the hydroxide ion molarity is 10th molar or greater. You think you're going to get a molarity of hydroxide ion in this which approaches 10th molar? You'll get a hydroxide ion molarity in this which approaches about 1 times 10 to minus 6 molar. Woo-wee. Basic, but not very. What would you do if you were challenged with the problem of calculating the hydronium ion concentration for this solution? I will tell you at this stage of the game, you don't know how to do it yet. For starters, you'd have to realize that the principal acid-base equilibrium in this system is established by reaction between ammonium ion and hydrogen carbonate ion. The best acid, the strongest base as principal species. Products, quote-unquote H2CO3 and ammonia. Where the hell's the hydronium ion? It's not there. Yet we focused on the main acid-base equilibrium in this system. I guess we've got to look someplace else. And the someplace else is ammonium ion reacting with water, or hydrogen carbonate ion reacting with water, or both. And for this system, you'll find out that that both have to be considered. Makes this a tough problem. One which you cannot solve without charge balance. And we haven't done charge balance yet, so we'll put that one on hold. For now, from a qualitative standpoint, we are in position to realize the solution is mildly basic. We have done that, but not yet able to get the hydronium ion concentration calculated. But we'll get there. Won't be long. 1822. A sodium sulfide solution is mixed with a hydrochloric acid solution. The species, principal species in the sodium sulfide solution, sodium ions water, hydrogen sulfide ion, and hydroxide ion. Because on making the solution, on putting sulfide ion in water solution, the sulfide ion reacts with water to an extent of, practically speaking, 100%, and converts to hydroxide ion and hydrogen sulfide ion. So if you inventory this system as S2 minus AQ, you're wrong, and you lose. You can't do anything with that. Now, as we've already recognized, when you have to do a calculation on a system, then your inventories must be done quantitatively. So we have to write QPSI. So here's our QPSIs. Sodium sulfide solution, the hydrochloric acid solution. You can do the QPSIs. You can verify that these are the correct mole quantities of the indicated species in the solution. You did that stuff in 2045. So, we look at our inventories. Strongest acid hydronium ion, strongest base hydroxide ion. So we write the reaction equation. We know this goes, and practically speaking, 100%. Because K for this thing is 1 times 10 to the 14th. Wowzer. That's a big time K. And we also know that in running this reaction, we put together equal mole quantities of hydronium ion and hydroxide ion respectively. So the original quantities of hydronium ion and hydroxide ion that were combined in assembling this system have killed each other. They're gone. Now, some students at this stage of the game say, okay, I now have a system which is practically speaking pure water, so it's got a pH of 7.00. Wrong? Because any student who will have made that statement forgot to pay further attention to the PSI. You do that, you lose. When you're running calculations on a system, like the systems we are considering in Chapter 18, there's only one way to be successful with these calculations. And that is to keep your attention focused on what property of the system at all times? What? PSI! If you don't know what the hell's in there, you can't do chemistry with the system. Always pay attention to what you got. Because what you got determines the chemistry that happens. So I go back and look at the PSI as it now stands. I struck hydronium ion, hydroxide ion, but I still got this in there. So I get out my acid-base table. Are you looking at it? The acid-base table? You see that the formula for HS minus appears in each column. Acid column as well as base column. Aha! But the listing of HS minus in the acid column tells us that it is a weaker acid than water. But its listing in the base column tells us that it's a stronger base than water. So we now know, before we do any arithmetic, that this solution has got to be basic. Caused to be so by the presence of HS minus. So, to get this pH of 9.74, which is the answer to this problem, you have to get Kb for HS minus. Let's put it up here. How do we get Kb for HS minus? Kw divided by Ka for what acid? What acid? What's the conjugate acid of HS minus? No, no. H2S. Hydrogen sulfide. Which is on the acid-base table. KAH2S. Let me see if I can see it. 1.1 times 10 to the minus 7. Look right? Yep. How about that? I told you I see this damn thing in my sleep and I love it. See? So I divide Kw by 1.1 times 10 to the minus 7 and I get Kb for HS minus, which is 9.1 times 10 to the minus 8. And now, practically speaking, I have a single solute system because the hydronium ion hydroxide ions got murdered. So I can write this straight away. For this system, what does X represent? The equilibrium molarity of H2S, as well as the equilibrium molarity of hydroxide ion. Because KBHS minus corresponds to the equilibrium established by HS minus reacting with water to make its conjugate acid, which is H2S, and given that it's a base, it's reacting with water to make hydroxide ion. How do I get M sub I? Well, I have recognized from my QPSI inventory, I've got 1/100th of a mole to 2 sig figs of HS minus. But equilibrium calculations require concentrations. What's the molarity of HS minus in this system? Well, it's the mole quantity, 0.010 moles, divided by the volume of the system. What is the volume of the system? 0.30 liters, right? Because I put together, in making this mixture, 200 milliliters of one solution and 100 milliliters of the other solution, right? So, M sub I, HS minus, for this system is really tough arithmetic. And this KB value is tiny. Next comment, if you've not yet recognized this, when a with a K value is small relative to M sub I, as it is in this case. If a K value is small relative to M sub I, it's a good bet that M sub I minus X equals M sub I. And that applies to this case. If you can forget X in the denominator, put this in, take the square root, and get the hydroxide ion molarity, which corresponds to this pH. Then an important definition. We've talked about ionization. Now let's talk about ionization extent quantitatively. This is defined by the recipe that you look at on the board. Percent ionization is calculated by this recipe. A derived species molarity at equilibrium. If acetic acid reacts with water, and a water solution of acetic acid is the only solute, reaction of acetic acid with water makes hydronium ion acetate ion. Clearly, for that system, acetate ion molarity represents the molarity of a derived species. Because if acetic acid is your sole solute, the only way you can get acetate ion in there is if acetic acid gives away H+. Divided by the label on the bottle, the numerical value for the label on the bottle for the ionizing solute. So if it's 10th molar acetic acid, this is 0.1. You calculate the acetate ion molarity for, or determine the acetate ion equilibrium molarity for 10th molar acetic acid, put that molarity up here for acetate ion, 0.1 down here times 100% gives you ionization extent. Now then, based on stuff we've already discussed, you should now know, or should be able to tell me, not me, tell yourself, that's what matters. On what does percent ionization depend?
Intermolecular forces.
The K value?
Yes, implicitly, but the K value. How does ionization extent depend on K value? Is it directly proportional? The larger is K, the greater the ionization extent. Hey, that's what these K values mean, remember? KAs are values which reflect the strength of the ionizing acid solute. The larger the K, the greater is the ability of that acid to react with water and ionize. So if I got 1 molar hydrogen sulfate ion and 1 molar acetic acid, hey, the ionization extent of the hydrogen sulfate ion is far greater. Because its Ka value is 1.2 times 10 to minus 2, which is a lot bigger than 1.8 times 10 to minus 5, which is Ka for acetic acid. Now then, on what else? On what solution property does percent ionization or ionization extent also depend on? Beside magnitude of K, what else? Concentration. Does ionization extent depend directly on concentration or inversely? Inversely. Inversely, you betcha. The more dilute the solution, the greater is the ionization extent. So, on what does percent ionization depend? K and 1 over m sub I. Done. Problem involving such. Question 1824. If you did question 1819, you could determine that for 1,000th molar acetic acid, this is question 1819, the ionization extent of acetic acid is 13%. That having been said, for 1,000th molar acetic acid, what's the hydronium ion concentration? I'm listening. What's the hydronium ion concentration for 1,000 molar acetic acid? I want 13% of 1,000th molar. Tell me what that is. And I don't want to see any buttons pushed. What's 13% of this number? 1.3 times 10 to minus 4, which is also the acetate ion molarity. So if you take 1.3 times 10 to minus 4, divided by this number, multiply by 100%, that's what you get. If I asked you for 13% of 1,000, you'd all tell me right away. 130. But as soon as I start putting decimal points in there, I know what happens up here. The sparks start to fly. The short circuits begin to set in. The computer says reboot. Don't let that happen to you. Do not rely blindly. Do not be dependent entirely on this damn push button device. The best calculator you got by far is this thing. Use it. So, we're talking about an acetic acid solution for question 1824, for which it is stipulated that this acetic acid solution illustrates an acetic acid ionization extent of 10%. Okay? 13% for 1,000th molar acetic acid. That's question 1819. For question 1824, is m sub I for the acetic acid solution considered in question 1824, where the ionization extent is 10%. Is it greater or smaller than this value?
Greater.
Got to be greater, doesn't it? You all see that? Because the ionization extent is smaller. Well, we're talking about the same acid, so the ionization extent consideration can't relate to Ka. So it must be molarity. The solution with the higher molarity will have the smaller ionization extent. Will the solution with the smaller ionization extent have the higher or lower hydronium ion concentration? Higher or lower? Higher or lower? I hear a hung jury out there. Higher hydronium ion concentration and a pH that is lower. The damn solution is more concentrated. Right? What is the molarity of this solution? Well, here's our recipe. What are we going to write in the denominator? I got m sub I minus x. What is x for this solution? In this solution, where the acetic acid solutes ionize 10%, how does the equilibrium molarity of hydronium ion acetate ion relate to m sub I? How does the hydronium ion molarity and the acetate ion molarity relate to m sub I? How much of m sub I is it, the hydronium ion molarity and acetate ion molarity? It's 10% of it, damn it. We're told you that. So what have I got up top for x? And then I'm going to square it.
0.1
Ah! If you leave out this, game is over. And in the denominator, what do I have? What do I write here? 0.90 m sub I. So this goes away, and one of these goes away. And I calculate m sub I. What's the answer? I don't know. I don't give a damn at this stage of the game. Because I now have written what I need to write to answer the question, what is m sub I? And I know that whatever the value is, it's bigger than this. Actually, I do know. Done. You can do the arithmetic. We've done the chemistry. That's what counts. And now to our solution, for which the K value for the solute is 1. This corresponds to K 1.0, 2 sig figs. This corresponds to hypothetical acid HA. At the minimum, the arithmetic we're now going to do will show you why the statement I made last class was a blunder. I make blunders. I don't want to make them, but I do. Please, if at any time during our class conversations or after you look at the video on Absolutely Chemistry, if you have cause to believe that I've made a blunder, you better holler. The hardest work to proof is work of your own. If I've written something in the notes which you think is wrong, you holler. Tell me. It's the easiest way to call my attention to it. When you take quizzes and exams, if you had a question mark wrong, because we said you picked the wrong answer, and you think you've got the right answer, don't be bashful. Say so. Because I make mistakes. I don't want to make them. And I will not penalize students for my mistakes. That's not fair at all. But sometimes I make mistakes, you get penalized, and I don't know that I made the mistake. Well, then you're going to pay a false bill unless you speak up. Yup! Speak up! Don't be bashful. Ha ha! Flex that intellectual chemistry muscle. All right? Here we go for this solution. Now then, do you think this is a situation for which m sub I minus x equals m sub I? You see that for this system, Ka and m sub I are equivalent? Each 1.0? Clearly then not a system for which m sub I is a lot bigger than Ka. So from an arithmetic standpoint, that's telling us that I have to treat this like a quadratic. I have to recognize that m sub I minus x does not equal m sub I. So how do I solve this? Do I get out my quadratic formula grinder? Not in my presence. You do it based on chemistry. And the chemistry that I want you to base this solution on is the chemistry we just talked about. I want you to think about a percent ionization which will satisfy this Ka value of 1.0. So for house solve, we're going to write down, for a problem like this, speculate on percent ionization. Now, if I'm going to speculate on percent ionization to solve the problem, what percent ionization value should I speculate on first? 50%. Why 50%? Well, if I speculate on 50%, how does x compare to m sub I? half of m sub I, isn't it? Isn't 50% of something half of something? Good. And this is 1.0 molar HA. So up top I'll have 0.50 squared divided by 0.50. You see? That for a situation like this, the 50% speculation will give me a value for the fraction that's half of m sub I. How does 0.50 compare to 1.0? Smaller. So you see why what I said here was a lie? The ionization extent for HA in this solution has got to compare how to 50%? Got to be bigger than 50%. So I'm simply going to tell you, because we already mentioned here the way to solve this, 62% doesn't. The arithmetic would be 0.62 quantity squared up top divided by 0.38. Because after 62% of 1 molar disappears, this is how much you got left. And if you grind this out, what do you think it equals? 1.0. Done. Now, another takeoff on this percent ionization speculation method. Question 1826. Now let's look at 10,000th molar acetic acid. Well, let's go back and look at this for a moment. Where we have here recognized that for 1,000th molar acetic acid, the ionization extent of acetic acid is 13%. So before we do any arithmetic here, by taking advantage of what we recognized here, we know that for this solution, the percent ionization for acetic acid compares how to 13%? It's bigger because this solution is more dilute. Okay? Secondly, is it possible for this solution that m sub I minus x is equal to m sub I? You see, for this solution, that m sub I and Ka are not too far apart numerically. Look what would happen if we neglected x in the denominator and tried to solve in that fashion. Well, we'd have 10 to the minus 4 times this, which would give us 1.8 times 10 to the minus 9. And if I take the square root of this, I'm going to get 10 to the minus 4.5. So I'm going to rewrite this as 18 times 10 to the minus 10. Give me a gee whiz square root for 18. What's 4 squared? 5 squared. So the square root of 18 is closer to 4 than it is to 5. You agree with that? The answer is 4.2 to 2 sig figs. So based on hydronium ion molarity, which is acetate ion molarity, which is X, I would get a value of 0.000042. And if I take 0.00042 and subtract it from m sub I, what value do I get? I get 0.00006. which means I have reduced m sub I by at least 40%. So m sub I minus x is hardly equal to m sub I for this problem. So, as I recognize there, I must also realize here, to solve this, I got to keep x in the denominator. I've got to treat it as a quadratic, but I sure as hell won't solve it as a quadratic. How am I going to solve it? Percent ionization.
50%.
What should I try first? 50%. But notice we've already tried 42% and found out that's too big, didn't we? That's really what we did here. Okay? Remember? But we'll write it down anyway. Try 50%. That gives 5 times 10 to the minus 5 quantity squared over 5 times 10 to the minus 5. How about that? Remember the arithmetic simplicity of trying 50% ionization extent first. You always get half of m sub I. And half of m sub I, which for this case is 5.0 times 10 to the minus 5, compares how to Ka? It's bigger. 5.0 times 10 to the minus 5 is bigger than this. How about almost 3 times as big? Because you got about triple this to get up to 5. Of course, you triple this, you get 5.4. That's why we said 5.0 times 10 to the minus 5 is about triple this. I know I'm doing stuff with numbers which, until this point, you probably haven't done before. So I plead to you, I command you, dust the cobwebs off this wonderful computer and get it to work in the way it's capable of working. You know how to play the game now. 34% does it. What will we get for 34% from a number standpoint? We'll get 3.4 times 10 to the minus 5. Quantity squared. What do we get in the denominator? What is it? 6 point?
6.
Grind this out, you get 1.8 times 10 to the minus 5. Next conversation, indicators and buffers. So after you ace quiz 1 tomorrow, then you take a lunch break, and then you study indicators and buffers, right?